Alright, so this section is about something known as the definite integral. And what we're going to do is relate the area that we've been doing from section 5.1 to this concept of a definite integral. So I'm going to start down here using the left and right endpoints because those are the examples we've been doing. So I'll say that we know that area is equal to the limit as n goes to infinity of a sum I equals 0 to n. I guess it's 1 to n that we talked about if we're using the right endpoints. F of xi, and then times delta x, where this is that width that we talked about. So delta x is that b minus a over n that we've been using. So it's just another way to write that in a sort of cleaner form. So this is the area function that we talked about from back in section 5.1, and we'll come back and do a few more examples from 5.1 next time in class. But this is that thing we were doing. We took the right endpoints, we said we're going to sum that from 1 to n, and we also, remember, every time needed to multiply by the width of each of those rectangles, which was delta x. And we're now going to write that. This is obviously very not very neat notation, so we want to write it in a cleaner way. And what we can do is use this integral sign, and we'll say we're going to, the area between a and b of some function f of x with respect to x is the definite integral. So this is what we refer to as the definite integral. It is an integral sign that has these two bounds on it that tells us where we're starting and stopping of calculating our area. And it is a representation of area. So when you see that, you want to think and imagine that you're dealing with areas. And in particular, we're going to look at the terminology now to understand exactly where that comes from. But I just want you to recognize that when you see this, what you're really thinking about is just adding up those infinite rectangles. A way to write that in a cleaner format is to write it with this integral sign. It's similar when we first started doing derivatives and we had the limit definition. The limit as h approaches 0, and instead of writing that every time we talked about the derivative, we just started using f prime of x. And so this is a similar concept with the integral sign. Is just an easier way to write this limit of the infinite sums of all those rectangles. So this is going to be our notation for finding area under the curve. So in particular, when you see this sign, we'll talk about the integral sign. This is an integral, so you'll hear me say the word integral a lot. And then this b up here, this is an upper limit. And then as well, there's always a lower limit. So that's what this guy is. And then this dx is really important. A lot of people will leave that off, but it's part of the integral and it tells us what we're going to integrate with respect to. WRT, with respect to. And we'll have to write all that out. So it's a common abbreviation we'll use. So the dx tells us that we're integrating with respect to x. In other words, we're going across the x-axis, building our rectangles. So that's pretty important as well. The other key thing about a definite integral like this that has these bounds, a and b's are numbers. Remember that this definite integral is going to equal some number. Okay, so a definite integral will always give us a value back, so make sure when you get your final answer that it is an actual value and not some other weird thing that's not a number. That is what a definite integral is doing. It's calculating some form of an area, and so you want to make sure area has a number associated to it, and that's what you're actually calculating. And in particular, when I talk about area, as long as our function is always positive, so that's what this statement here says, right? If our function is always positive on the bounds that we're integrating, then this integral from a to b of f of x dx is going to give us the area under the curve. The curve f of x from a to b. So as long as the function is positive, that's exactly what this integral is calculating. It's calculating area, no question. Sometimes, though, you might have a function, for example, that goes above and below the x-axis, and you're calculating the area for that. So between here and here, right, you'd have some area above and some area below. And so in that case, we would say that the integral from a to b of our function is equal to some a1 minus a2, where a1 is the area above, and A2 is the area below. So in other words, this is sort of the net area. So, and you want to think about, in general, the integral is the net area. So if it's all above the x-axis, then obviously you won't have anything here. The A2 will be 0. But if you have some above and some below, then you'll take the area sort of like in this case, this would be sort of the A1. And then down here, right, that would be your A2. And then you subtract the negative area pieces from the positive area pieces. So you can get a negative value for these definite intervals, depending on how much area is above and how much area is below. One other quick thing before we work this example, so this has nothing to do with the example. When you see an integral, so the integral from a to b of f of x dx, it doesn't matter what letter is inside of there. So you can change this out as long as you continue to change both the function and the d, the thing that you're integrating with respect to. So just keep in mind that this variable, as long as these two things match, it doesn't matter what letter you use or what variable you choose. So feel free to use any variable or any letter that you want. They're all the same, they're all asking the same question. So now we're going to look at this particular example. So we're going to use this example. We'll do it in red to distinguish it from our little note that we made that doesn't necessarily have to do with this particular example. But we're going to find the integral of this, so from 0 to 2, of this particular square root function using area formulas. So that's what all we're talking about in this section is area. So if we try to draw this picture, hopefully you maybe recognize this. It might take you a minute, but with this square root and a 1 minus x minus 1 squared. So if you don't recognize it, what you can do here off to the side is say if this is my y, oops, let's see here, if this is my y, x minus 1 squared, square root of that is equal to y. If I try to like rearrange this a little bit, you might notice that this is this, and then if we move some stuff around, we get y squared equals x minus 1 squared. Or, sorry, 1 equals y squared plus x minus 1 squared. So hopefully now if you have it rewritten like this, hopefully that is something that you can recognize. And that is a circle that's centered at 1, 0. So the center of this circle is right here with a radius of 1. So we know that it's going to come out this way and over here and over 1 this way. And so do this. And it's only the top part of that circle because it's the positive square root version, right? We actually don't have the bottom part because of the fact that the actual original integral only had the positive square root of that, because I did square both sides to kind of figure out what the shape is. So in general, when you see something of the form square root of 1 minus an x squared or something minus an x squared, that is a circle formula, and you just want to think about what circle are you dealing with. And in this case, this is the circle we're dealing with. And we're going to go from 0 to 2, so we are actually going to find the full area of this circle. So what this question was asking was, here's our formula. You may not have recognized that as a circle, but from now on you should recognize things of this format, a square root with a 1 minus something involving an x squared. That is a circle format, or even a 7 minus x squared. It tells you where the circle is centered and that this is only the positive or half portion of the circle. And then once you draw that circle in, then you can just say, hey, I know the area of this, right? This is a circle with radius 1, so my area of this is really just 1/2, because it's half a circle, pi r squared. And in this case, my r is 1, so I think I get 1/2 pi. So that's what's going to be the answer to this integral. For this answer here, it's 1/2 pi, because that's what that integral is asking, is to calculate the area. So next, I have one more picture to show you to practice with area under the curve. And then in class on Monday, we'll take some time to actually work with some of the properties of integrals that just deal with areas, and do a whole bunch of examples with that. But for now, I just want to make sure we understand that the integral is really just an area function, and we're just calculating area. So let's say we have this particular picture here. So again, we have a circle of radius 1, and then let's say we have a little piece that goes up here 1 maybe. So let's say this is our picture and it wants us to find the area under the curve from 0 to 3. So again, the area under the curve, right, is just the area of this circle plus the area of the triangle, right? So that's all that we're asked to do here. So if we were asking to find the area, it looks like the area is just going to be, again, pi over 2 times 1 squared, because it's just half a circle. And then here, this is a triangle, right? 1/2 base times height, where both the base and the height are both 1. So that gives us an area of pi over 2 plus 1/2. So in other words, if this is our function, like if this curve was our f of x, what you could say, right, is the integral from 0 to 3 of our function with respect to x, because we're integrating with rectangles along the x-axis, is pi over 2 plus 1/2. So that's another way to think about it, right, is that that's what that symbol now represents for you, hopefully for now. Just keep in mind that that's what that symbol is representing. It's representing area under the curve, and that's exactly what we're trying to calculate. So I just want to sort of preview to you a little bit in class. So these 8 integral properties, I will print these out on a piece of paper, and we're going to go through and do some examples related to these integral properties. So let's just go through these 8 or 9 now, so you kind of have a sense of what all the properties are, and then we'll use them in class and make sure that we understand what all of them say. So the first one says that if we integrate from a to b of some function, that's the same as integrating from b to a of another function by putting a negative in front of it. So one way to think about that is if we have our picture of area up here, and here's our function, and we're going from a to b, right? This way we're building our rectangles this way and adding them up, right, and taking all of our areas. But the other way, we're starting from b and moving in this direction. And so all of our links are kind of negative, right, because we're going the opposite way. So whatever we're doing from a to b, if you want to flip the bounds, then you have to change from a plus to a minus. So that's where that minus comes from. The next thing is if we have a function and we just integrate from a to a, so if we go back and look at this same picture, if we integrate from a to a, what is the width of any rectangle that we build there? That's kind of the question you want to think about. And if you think about that, the width is 0 and the height is whatever it is, but that tells you that the area for that piece is going to be 0. So if you just integrate from a to a, there's a 0 width there, so 0 times whatever height that you have is going to be 0, and so we get 0. This next one talks about integrating a constant, and this one's pretty nice to think about a picture. So a constant function, remember, is just a straight line. And then if we're integrating that from a to b, you'll see that we're calculating this area right here, which hopefully you recognize is just a rectangle. And so this distance from here to here, that's b minus a, right? That's the width of the rectangle. And the height of the rectangle is up here to c, right? So c times b minus a. So if you're just integrating a constant function, you're just going to get back c times b minus a, where you have the width of b minus a and a height of c. Next up, these next 3 kind of deal with adding and subtracting of things. And again, I think it deals with just thinking about area. So, and you can think about summations as well if you want to think about those sums that we were doing. If you have f plus or minus g and you want to find the area for that function, that's really the same as finding the area of f and then adding or subtracting it to the area of g. And I think the one that makes sense for me to think about that is to think about the fact that these are really just summations, right? And if you have a sum of some pluses or minuses, you can break that into 2 sums. You don't have to keep it as one big sum, and that's pretty much what number 4 is saying. So we can split into 2 pieces, and similarly, if we have a constant on the inside of our integral, we can take that to the outside. And again, thinking about that big sum, like if you have a c inside of a sum, so if we had some c, I think that was one of our summation properties. If we have c inside of the sum, then it's c in times every single one of these things, right? And so you can always take that c outside of the summation sign. And so since you can take it out of the summation sign, you can also take it outside of the integral, because the integral is just an infinite limit of a sum. This next one is pretty great. If you have a function and it's going from maybe a to b and then from b to c. So obviously if we take this area from a to b and then we add it to this area b to c, that's the same as just taking this full area from a to c. So that's what this one is saying. So as long as these 2 bounds here match up, right? The top bound from the first one and the bottom bound from the second one, you can squish those together and just say you have the area from A to C. So it's another property of integrals. It's just thinking about things related to area. If we have a function that's always positive, then the area function is also going to be positive, right? No question about that. Number 8 is if one function is bigger than another function for all values between a and b. So if there's one function that's always taller than another function, then certainly the area under f, right, is going to be bigger than the area under g. So that's what this one is saying here. So hopefully that's pretty obvious. And then the last one, again, a picture is always helpful for these things. If you have some upper bound capital M and some lower bound lowercase m, and your function is somewhere in between here, so here's our f of x, between a and b, then it turns out that if you think about calculating this area down here, right, m from a to b, that's certainly going to be smaller than the area under f, right, the area under f being this part here. So the area under f will certainly be larger than that since f is always bigger than m. But it'll certainly also be smaller than if we took the area of the full rectangle that was taller than f. So that's kind of what this one does, right? It calculates the area of those rectangles, the smaller one below f, the bigger one above f, and says, hey, well, the area for f has to be between the area of those two rectangles because its values always lie in between those two things. So be ready to work with these integral properties next class period, and we will talk a little bit more about section 5.1 as well before we do some examples from this section 5.2.